So, chapter or section 8.1 is to talk about series. You have to talk about sequences first. So let's just right off the bat, let's just say what is a sequence and what is a series? Because when it starts getting hairy and complicated, you have to have that basic understanding in place, or else you'll be really confused. So let's just, and I'll keep reminding you. So a sequence is an ordered list of numbers. Okay, a sequence is an ordered list. Okay, a series is the sum of the entries in the list. Okay, so for example, 1, 3, 5, 7, 9. What's that? A sequence or a series? This is a sequence. It's a list of numbers. So then what would be the associated series? 1 plus 3 plus 5 plus 7. Okay? So that's the associated series with this sequence. Sometimes we get so wrapped up in these complicated problems, and we're learning the rules, we're memorizing the rules, we're trying to figure out what case we have, and we forget really what we're dealing with. And this is what we're dealing with in this chapter. A sequence is an ordered list. And a series is, if you're taking a series for a particular sequence, it's just adding up the elements in that list, or the members of that list. Okay? So when we say an ordered list, we're saying specifically this is the first entry, this is the second, this is the third, etc. So we use n to denote which entry of the list it is. Term. Okay, that's the word I'm looking for. I'm calling them elements and numbers. Term. So this is which term it is. So what is the fourth term of our sequence? What's the fourth term? 7. Okay, so when n equals 4, that's the fourth term, and it's the number 7. So then our sequence is denoted A sub n. So meaning A sub n is the nth term of this sequence A sub n. So A sub 2 is what? 3. A sub 2 is 3, and that is which term of the sequence? Second term. Okay? So A sub 2 equals 3, which is the second term of the sequence. So we start by focusing on sequences, learning some of the ins and outs of sequences, and then we move to series. So I wanted to start off by just distinguishing between sequence and series right off the bat. So once we get on that foundation of sequences, then the focus of the chapter is on series. Okay. All right, so then, so A sub n, like we said, is the nth term of a sequence. And we can write it as like in set notation. So it would be A1, A2, A3, dot, dot, dot. You can say AN minus 1, AN, AN plus 1, dot, dot, dot. So if you're talking about the nth term of the sequence, then the term right before it is the n minus first term, n minus 1 term. And the term right after it is the n plus first term. Okay, so for this sequence that I put up there, can you figure out a formula for the nth term? So an expression, given that you're talking about the nth term, if you're talking about the fourth term, then this formula would generate the number what? 7. And if you're talking about the third term, that formula would generate the number 5. So everyone see if you can do it. So can you come up with a formula that takes whatever n and gives you the correct nth term of this sequence, 1, 3, 5, 7, 9, etc.? Can you do it? So for instance, n cubed minus 2 plus the square root of n. Does it work? How can we test it? Let's look at a sub 2. What's a sub 2? Well, it would, according to this, it would be 8 minus 2 plus the square root of 2. 8 minus 2 is 6. 6 plus the square root of 2. How did I do? Really bad, right? Really bad. But that's an example. Something like this, a formula with n's in it, that if I plugged any given term number in, it would give me the corresponding term of the sequence. Anybody think they got it? Okay, one person thinks they have it. Anybody else think they have it? It's pretty simple. Maybe if we do a few more, it would help. Let's do 6, 7, and 8. I think for bigger numbers, you can start to see it a little bit easier. So for 6, it's going to be 11, 7, 13, 8. Yeah, I think for the bigger numbers, maybe you can see it a little easier. How many people think they got it? Raise your hand. Just 3? 4? 5? So what do you do to 8 to get 15, 7 to get 13, 6 to get 11?
Double and subtract 1. 2 and minus 1.
Yeah, double, you double and subtract 1, right? So the formula is? 2n minus 1. It's always 1 less than twice whatever n is. Okay. Questions so far? Can I turn the page? Ready to go on? Okay, so other examples? So this is the kind of thing that we're going to see, right? So we get these formulas that are generating the list. N equals 1, n equals 2, n equals 3, and then for each n, this will generate that term of the list. And it doesn't have to be A, you know, so we can name B event, C event, D event, it doesn't matter. We can use any letter. So these are all examples of sequences. All right, so pick one. Just pick any one you want and write the first 3 terms, okay? Just pick, everyone pick one and write the first 3 terms. Don't everyone pick the first one. Anyone pick number 2? Tell me the first one.
1 was -3.
1?
Sorry, -3.
-3 is the first? Is that what you got too?
I didn't try it, but I tried the first one.
-3 is the first term?
Yeah.
Okay.
And then 5/4.
5/4, is that next?
And then -7/9.
So notice this one has this -1 to the n, and what is that doing to the sequence? Makes it alternate signs, right? So when n is positive or n is even, you're going to get a positive value in the term in the sequence. When n is odd, you get a negative. Okay, so that's one way to get this is called an alternating sequence. Alternating sequence. Okay, anyone do the last one? Tell me, Tina, what was the first?
First one got
1.
And then just tan pi over 2. This gives me 1.
Oh, okay, I didn't mean, so that's not a good example. Let's see. So what do I want? I want 2n minus 1 times pi over 4. Sorry, bad example. What I meant was 2n minus 1 times pi over 4. Now try it. So when n is 2, you get?
And you get 1. Okay.
You should get -1. You get -1? Is that right? And then when n is 3, you should get 1. Is that right? Is that what's happening? Here? Yeah, it is positive.
Oh, sorry.
Yeah, it is 1, yeah. Yeah, so when you're basically taking 1 times pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, this is that sequence. So here, look, here's another way to make it alternate, right? Using tangent. Tangent, so there's a way to make it alternate signs using tangent. So, but the most common way is this the easiest, most common, -1 to the n. Okay, so sequences and functions. How are sequences the same as and different from functions? What do you think? How about the same as? What's the same about a sequence as a function? I know Adam knows.
You have input and an output.
Okay, he's talking about input and output. Do sequences have input and output? What would be the input of a sequence? The term n, right? So what term? You just where are you in the list? What number in the list? And then the output would be the actual term. Okay, exactly. So that's the biggest similarity. There's this input and output relationship. Okay, and what's different about functions? It's different from sequences from this kind of common functions we talk about. Yeah.
Functions are continuous.
Okay, so can you say more? What do you mean?
So like how we had the alternating functions up there, if you were to graph that, then it would be continuous.
And just like, what does that mean to you? Continuous.
Like if you were to graph it, it would make a line.
Okay. So, meaning we include values, a continuous stream of values. Say not only input values that are the counting numbers, but everything in between as well. So let's look at these. Here's a function 1 over x squared, and then we can compare it to the sequence 1 over n squared. Right? So these have the same input-output relationship, right? Input is x here, and is our term number here, and then the output would be 1 over the input squared. So what does 1 over x squared look like? You know? Yep, so it's close to 0, it's large value, and then as we get large, it levels off. Is that it? Is that the whole function? Okay, but is there more to this function? Yeah, what when x is negative? Down here, like this?
No, positive.
No, it's going to be positive, right? It's going to be positive because it's squared. So it's going to be a reflection across y. So that's 1 over x squared. And so then what would 1 over n look like? Instead of x, we have n, and then we have a sub n. So what would this look like? The same or different? What's that?
Points.
Points, right? So points. What's the first one? 1. And we get 1, comma, 1. And then we'll get 2, comma, 4th. And then 3, comma, 1/9. So is it the same or different than 1 over x squared? Yes. Right? It's the same in that you're getting the same output for the same input, but different in that you have this only the numbers 1, 2, 3, the counting numbers, or the natural numbers, are the domain. Right? These are called the natural numbers. They just are used to count, right? And that's all we have in a sequence. The first term, the second term, the third term, the fourth term, we're just counting, right? So the domain of our sequence is the natural numbers. What's the domain of this one? Well, it's all real numbers except, right? But for for those outputs, for those inputs that we have in the sequence, the outputs are exactly the same, right? So when x is 4, we get 1 over 4 squared, just like in the 4th term of the sequence. Okay, so we're going to think about sequences in terms of functions, right? So whatever this function does, as x gets very, very large, is the exact same thing the sequence will do as x gets very, very large, right? Because they're going to have the same outputs. So we look, what is that the idea of? That's the idea of limit, right? So the limit as, say, x gets really big of f of x. What is it? 0. And so if the limit of the function as x gets really big is 0, then the limit of the sequence as n gets really big is 0. That should make perfect sense. So we use our finding limits of functions to find limits of sequences as well. Okay, can I go on to the next page? We're good? Okay, so definition. A sequence is convergent, so we saw this idea before. Convergent versus divergent. We saw that when we did improper integrals, remember? If the limit as n gets really large of a of n exists. Or in other words, the limit equals some value called L. If that's not the case, if the limit does not exist, you don't get a actual real value for the limit, then this sequence is called divergent. And again, to determine these limits of these sequences, we're going to look at the limit of the corresponding function. It's like one and the same, right? We look at the limit of the parallel function, or the function that's just like it. And so so basically that's the theorem here. So theorem. So let n be a natural number. If you have some function whose limit exists, and the nth output, or the output of the function when x equals n, is the same as the nth term, then the limit of the sequence is L. So that's what we're saying here. If you're talking about a certain sequence, you find that equivalent function. If that function has a limit that exists or is convergent, then the sequence is convergent to the same value. Okay, so for example, the limit as n goes to infinity of 1 over n to the r. So what do you think that equals? 1 over n to the r. So we got 1 over n squared, 1 over n to the fifth, 1 over n to the first, 1 over n to the 20th.
0.
Will that be 0? Okay, so it depends on r. So yes, we're going to talk about these being. So what does r need to be for this thing to be 0? If r is what? So what if r is 1? Is it 0? 1 over n? Does that converge to 0? One half, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9. Does it converge to 0? If you're shaking your head, are you thinking of the sequence or the series? Are you thinking of the sequence or the series? So if r is 1, we're talking about this. So if you take it far enough, you get to numbers like 1 over a googol, right? A googol is 10 to the 100. Does it equal 0? Or does it converge to 0? If we take 1 and split it up to 10 to... But we're taking a unit, and we're saying what is the size of a piece such that this many pieces makes up the unit, right? Is that going to infinity?
You're taking the Google root of Google.
Not root. It's just if I have a pie and I've got a Google number of people and each person's going to get a piece. This is the size of one piece. I've got a gazillion people, and everyone's going to get an equal share of the pie, and we're talking about the size of each piece. Are those going to 0? Yeah. It's going to 0. It's really super, super small. It's like we keep breaking this up into more and more pieces and measuring the size of each piece. More and more pieces, more and more pieces, more and more pieces. Eventually, the size of each piece will be 0 if we kept going, right? Or would converge to 0. Okay, so what about 0.5? If these were all square rooted, say, r was 0.5. How about that? Does that go to 0? So when I get to, when n is a googol squared, 1 over the square root of googol squared is 1 over a googol. So eventually I'll get to 1 over a googol. Is it going to 0? Yes. So all r has to be is what? Positive. As long as it's greater than 0, the sequence 1 over n to the r will converge to 0. Okay, so that's number 1. Number 2. Now notice, here our term number is in the base. Here it's the exponent, p to the n. Okay? That equals 0 if, so can we think of when that would equal 0? So basically we're saying take some number, you're going to start with any constant, right? Any constant. And each time you go to the next value of the sequence, you're going to multiply by that constant again. So one more time than the time before. So we're going to say take a number, and then you're going to square it, and then you're going to cube it, and then to the fourth, and then to the fifth, and then to the sixth, on and on and on. So you're going to, whatever term number you're in, you're going to take our constant, multiply together that many times. When will that give you 0? Certainly if p is 0. Anything else?
Between -1 and 1.
Between -1 and 1. So like 0.5. You ever done this on your calculator? You go 0.5 and you go times 0.5 times 0.5 times 0.5 times 0.5 times 0.5. So you keep multiplying by 0.5 one more time over and over again. Does that converge to 0? Yeah. Right. So as long as you have a fraction number, something that's not, so for p between 1 and -1, so some fraction of a unit, you keep taking a fraction of a fraction of a fraction of a fraction of a fraction each time you go to the next in the series. Okay? When would this equal 1? When would it converge to 1 if p equals what? 1. Right? Because 1 times 1 times 1, you just keep getting 1, right? So if p equals 1, then this sequence is just 1, 1, 1, 1, 1, 1, 1, 1. Any other value, and this thing diverges. Okay, so if that constant is between -1 and 1, like 0.2, or say 1/4. So we're saying 1/4 to the 1, 1/4 squared. This is the sequence. 1/4 cubed, 1/4 to the 4th, 1/4, etc. So we're going to keep going. We keep every time we go to the next term, so we multiply by 1/4 one more time. We keep taking a quarter of what we had before to get the next term. So that's going to approach 0, right? That's, you keep taking a quarter of what you had, then that's going to approach 0. And that's because p is in this range here, right? So this is like exponential functions, right? Your input is your exponent. So what about if p were 2? What would happen if p were 2? So write out the first 5 terms of the sequence if p is 2. If it's p to the n. So write out the first 5 terms of the sequence when p is 2. Okay, what'd you get? First term is? 2, then 4, 8, 16, 32, 64. Convergent or divergent? Of course this is divergent. Badly, right? Badly divergent. Just gets huge really fast, right? Okay, so then given a sequence, determining if it's convergent or divergent is a combination of writing out some terms and looking at it and using common sense, and then applying some of these rules, seeing if one of the rules applies, and then kind of some ingenuity and algebra and like I said, common sense. Okay, so let's just look at a couple examples here. And so the idea is determine if it's a convergent or divergent sequence. So we'll just, to mix it up here, use some different letters. So say example A, Cn equals B. This is kind of a neat one here. Okay, so what I want you to do is I want you to write all these down first before we start working on them, because I'm going to use my. Actually, I can do it on the house computer. Yeah, no, I'm going to use my computer for something else. So I want you to write all these down, and then 0. Okay, next one. So 1 over 5 to the n. We could say 1 over 5 to the n as, so this is one way to state it like this. Say that. Oh, you're right. No wonder it looked funny to me. Oh, I hope that doesn't screw up the video. Okay, should have. Let's do this. No, it's fine. We'll figure it out. Okay, so what did I say? So 1 over 5 to the n. So that's saying it's convergent to 0. So that would be one way to express the answer. Okay, B, convergent or divergent?
Convergent.
To? Okay, and how did you find that out?
Because n gets really, really big. The minus 1 and plus 1 in the numerator and denominator negligible.
Okay.
So essentially just be n squared over n squared.
Okay, so we got n squared minus 1 over n squared plus 1. And he's saying, essentially, as n gets really, really big, the minus 1 and plus 1 kind of fade away. And you just have n squared over n squared, which is... So this was a principle you had in pre-calc for, what, rational functions. So we could write the equivalent function, which would be x squared minus 1, x squared plus 1, and it's just looking at the limit as x gets very large of f of x. And do you remember what you did? If the degree of the numerator and the denominator was the same, then essentially that limit would be the ratio of your coefficients. And if the limit of the function is 1, then the limit of the sequence is 1. Anyone do it a different way? So there's a technique that's going to be really useful on a lot of these problems. Anyone use it from Calc 1? Yeah, so the L'Hopital's rule says that if you have the limit of a function, of a rational function, if it has the form 0 over 0, so let's review, forms for L'Hopital's rule. Okay, 0 over 0. Infinity over infinity, 0 times infinity. I think there's one more. Can't remember. But those, basically, if you can set up a ratio, you're going to either have 0 over 0 or infinity over infinity in terms of your limit. That's when you can apply L'Hopital's rule. And that says take the derivative of the top and the derivative of the bottom, and the limit of that ratio will be the same as the limit of your original one. Right? So if we took this new function, say, called it g of x, it's a different function, and it's going to be the derivative of the numerator, which is 2x, divided by the derivative of the denominator, and that equals 1. So what's the limit as g? The limit as x gets very large of g is the same as the limit as x gets very large for f. So it's 1. So the limit equals the limit And so that limit for the g function, the function we found by taking the derivative of the numerator and the denominator, is 1. Therefore, the limit of our sequence is 1. So L'Hopital's rule is going to be important for these. Okay, what was the next one? N squared over n plus 1.
Divergent.
Divergent. And you could use, this would be another one where you could use L'Hopital's rule. How did you, so Luis, how did you come up with this? How did you come up with divergent?
Well, I just split down the points and saw that it was just going to infinity.
Okay, so you made the list. Yeah, you just started listing the values. So it was 1/2, then 4/3,
9/4, 16/5, and 25/6.
Okay, so we can just by observation we can see that these are increasing, but they're not leveling off, right? They're increasing, and the jump is getting bigger, right? The amount of increase is increasing, so that's gonna diverge. This sequence is gonna get infinitely large. Okay. You could also use L'Hopital's rule. It will show the same thing. You get 2n over 1. And so 2n is clearly a divergent sequence. 2n. Okay? D, next one. So again, you could write the sequence out, and you should have gotten 0, -1, 0, 1, 0, -1, 0. Is that what you got?
Yeah.
Divergent or convergent? Divergent. So some divergent sequences, they just get really big, bigger than, as big as you want. Other divergent sequences, they just hop around and they never get so close to a value that it's negligible, like the same as the value. Okay, so this is divergent because it's just going to keep jumping. It's not going to hone in or zoom in on a value. Okay. Pi over n to 3 over the n. Okay, this is divergent because it's the same as, so pi over n over 3 over n is the same as pi over 3 to the n. And what's pi over 3? Greater than 1. So this is that p to the n sequence, right? P to the n sequence. P has to be between -1 and 1. And here, P is a little bit greater than 1. Was that the last one I gave you?
Yes.
Okay. Questions on these examples? Okay, let's do some more. More examples. Divergent or convergent? So we have to have a little algebraic prowess here. What is 3 to the n plus 2 the same as? So we need to be able to write this. We should know what 3 to the n plus 2 is. So this is telling us how many times to multiply 3 together, right? So it's the same as multiplying 3 together, what? N times? But then, how many more 3's? 2 more 3's, right? If you're multiplying 3 together n plus 2 times, you can multiply 3 together n times, and then multiply by 2 more 3's. Does that make sense? So 3 to the n plus 2 is the same as 3 to the n times 3 squared over 5 to the n. Okay, now we can apply that little trick that I did in the last problem. What can we go from here? Do you see it? What can I do to this now? Same thing as the last problem.
9 times.
9 times, okay, 9 times what? 3 over 5 to the n. So, 3 over 5 to the n. Converge or diverge? Convergent to what value? This is that thing where you're going to go in your calculator. 3/5 is 0.6, right? You're going to go 0.6 times 0.6 times 0.6 and just keep it times, equals. And you're going to get the next term in the sequence each time by continually multiplying by 0.6. What's going to happen in your calculator? 0, right? Eventually you're going to get zeros. Well, what about 9 times that? 0. Convergent to 0. Convergent to 0. Okay, another example. How about this? Nope, cosine squared n. Cosine n squared, basically. Okay, what can we make of this? Observations, thoughts. I didn't ask for answers. I asked for thoughts, observations.
Cosine doesn't have a coefficient. Only gets as small as -1 and the largest +1.
Okay, cool. So cosine n, he's saying, will be between what? -1 and 1. So what about cosine squared? What will that do? Stay between 1 and 0, right? So, what about cosine squared n over 2 to the n? What will that stay between? Not 0 and 1. If cosine squared is less than 1, then cosine squared n over 2 to the n is less than 1 over 2 to the n. Right? And this is greater than 0 over 2 to the n, or 0. So our sequence always stays between 0 and this other sequence, 1 over 2 to the n, or 1/2 to the n. What does that do? As n gets big, that goes to 0. What's that? That is 0. So what about this? It should make perfect sense. This thing is always between, it's sandwiched between something that's going to 0 and 0 itself, right? So here's 1 over 2 to the n going to 0. Here's 0. And that thing's always in between those two. So it's got to go to 0. It's called the squeeze theorem. I won't write it out formally, we don't have time, but this is the idea of it. If the sequence you're given is always between two convergent sequences, if every value is between two sequences that you know that converge, then that one converges. I'm sorry, they have to converge to the same thing, right? So if your sequence is between two sequences that converge to the same limit, then yours converges to that limit. It gets squeezed between, stays between, so it has to go there too. So it's not good enough that these two just converge. They have to converge to the same thing. These both converge to 0, therefore ours converges to 0. The one that's always in between. That's the idea of the squeeze theorem. Okay, another example. A couple more. Okay, what about this one? So we need some, again, some algebra, some reasoning. How can we start this one?
Separate question.
Yeah, so if you've got multiple terms in the numerator and a single denominator, we can pull this apart, right? You can't do that with a sum or difference in the denominator. But we know that we add and subtract with a common denominator, so we can go backwards and pull apart fractions with a common denominator. So we got e to the n over 4 to the n minus 1/2 6 to the n over 4 to the n. Keep going. Who can go on this one?
Make the first one just e over 4 to the n.
Okay?
Minus 1/2 6.
Okay, so then, what do we got? E over 4 to the n. Conclusion. Remember what E is? 2.71828. About 2.7. Conclusion here.
0.
Conclusion here. 3 halves times 3 halves times 3 halves times 3 halves. Always multiplying by 3 halves.
Infinity.
Yeah, you're always making it 50% bigger than it was before, right? If you're multiplying by 3 halves by 1.5, it's always 50% bigger than it was before. So this is... So how about this? So this is going to get really, really small, and this is basically going to go to negative and get very large negative. Conclusion? Divergent. Who's going to win this? Who's going to win this battle? 0 or getting really large negative, right? Because you're actually subtracting, right? It's because you're adding. If it was 0 times negative infinity, well, then you have the Hospital's rule, right? So you have two terms multiplied, and one is going to 0 and the other is going to infinity. Well, that's an indeterminate form. That's what you can use the Hospital's rule. Make a fraction out of it, and then use the Hospital's rule. Derivative of the numerator, derivative of the denominator. And then you get an equivalent limit. Okay, so then there's another thing that comes up in these they're called factorials. Factorials. Questions on these examples? So n factorial is where you start at n and you multiply by n minus 1, then n minus 2, and you keep multiplying down until you get to 1 and you stop. So what is 4 factorial? What is 2 factorial? What is 11 factorial divided by 9 factorial? These are no calculator, no calculator. All these without a calculator. Try those. Okay, what's 4 factorial?
24.
You should have gotten 24. 2 factorial is?
2.
2. Okay, without a calculator, 11 factorial over 9 factorial. 110. And so we got to think about what it means. 11 times 10 times 9 times 8 all the way down to 1 divided by, this is the way you have to think when you start getting into these more abstract ones. 9 times 8 times 7 all the way down to 1. So what happens with these is, in this case, 11 factorial has 9 factorial as part of it, right? 11 factorial has 9 factorial. Here it is. It's right here. It's hidden in there, right? It's like the tail. This is 9 factorial. It's hidden within 11 factorial. So you can think of that 9 factorial over 9 factorial as 1, leaving 11 times 10. Make sense? You got to have that. When you're getting to these factorial problems, you have to have that way of thinking. You've got to see that and be able to think that way. So let's look at this one, 21. Can you make sense of that? Okay, so how could we write out the numerator? So if we were thinking about writing out the numerator, what would it be? First term is, or first factor, 2n minus 1. Then what's the next thing that gets multiplied by? 2n minus 2, right? It's 1 less than that, right? That's how it works. You did 4 times 3 times 2 times 1. You start with 4, then 1 less, then 1 less, then 1 less. Okay, so 1 less, then 2n minus 3, all the way down to 1. 3 times 2 times 1. Okay? Denominator. First factor. 2n plus 1. Next one. 2n. Then all the way down to. So what happens? Notice, what's this right here? 2n minus 1 factorial is hidden within 2n plus 1 factorial, because once you get down to 2n minus 1, then the rest becomes 2n minus 1 factorial. So this is the same as the numerator. Do you see it? So what does this thing equal then? Equals? Yep. Which equals 4n squared plus convergent or divergent. And how do you know? Convergent or divergent. So this is the same. 1 over 4n squared plus 2n is the same as 2n minus 1 factorial or 2n plus 1 factorial. They have the same terms. When n equals 1, when n equals 2, when n equals 3, they give you the same terms. Does that converge or diverge? 2,
0.
because this was the first rule we talked about. And 1 over n to a value, as long as that value is positive, greater than 0. As long as your exponent is greater than 0, that will converge to 0, right? So that converges to, so certainly if 4n squared plus 1 converges, then 4n squared plus 2n, that's even bigger, it's going to be even smaller, right? That'll be 0. Okay, how was this last one? See if you can figure it out. So this is negative 3 to the n over n factorial. Converge or diverge, and can you show why it does converge or diverge? Let me actually, before we work at 32, I want to point out something on this previous problem. So it's 4n squared plus 2n. Okay? That is always less than 1 over 4n squared. So it's kind of a squeeze term idea. That because this really doesn't fit the form of that rule. The rule is 1 over n to the something. But if you add 2n, then you really got something that's less than, you have a bigger denominator, so it's less than 1 over 4n squared, which we know goes to 0. Since it's less than that, it's squeezed between 0 and that, right? Because this is always positive, so this is greater than 0, and it's less than this, which goes to 0, therefore that goes to 0. So the tricky part comes in when you have something like this. What about that? Well, that's greater than 1 over 4n squared. Squeeze theorem, exactly. Squeeze theorem doesn't work because it's bigger than something we know that goes to 0. That's not conclusive, right? So that's another conversation for another day, okay? So, but anyway, we'll work on this one now. Number 32. So right off the bat, inconclusive. Because we have something that's bigger than something we know converges to 0. This one Really, basically, we got negative 3 times negative 3 times negative 3. How many negative 3's do we have? N. N of them in the nth term, okay? So in the nth term, what do I have here? So if it's the nth term, then n factorial is n times n minus 1 times n minus 2 dot 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 down to 3 times 2 times 1. Okay, so these first three terms, negative 3 over 1, negative 3 over 2, and negative 3 over 3, that will be greater than 1. What is that? Negative 3. Is that negative 6? Negative 27 over negative 27 over 6?
Yeah.
Okay, but then what about all these terms? So then it'd be negative 3 over 4, negative 3 over 5, negative 3 over 6, negative 3 over 7. And so what about all these terms? These are all less than 1, right? So this whole thing is less than negative 27/6 times negative 3 over n. Oh no, it's just less than negative 27, yeah, times 3 over n. Because all these terms in here are going to be less than 1. So this is going to converge because we know that converges, right? That will go to 0, and then that's just a constant. And that thing goes to 0. And what we have is less than that, or closer to 0. The absolute value is less than that. Because all these terms in between, right, are going to make this even smaller than that. Because it's negative 3 over a number whose magnitude is bigger than negative 3. So again, since that converges to 0, and this thing is always, so we should say, the absolute value is always less than the absolute value of that. Therefore, ours converges to 0. Did you catch that? Does that make sense? Okay,